Have you ever stopped to think about the invisible systems that make our world run? You know, the ones that make sure water comes out of your tap or that the lights turn on? Well, today we're going to pull back the curtain on a tiny device that's one of the unsung heroes of all of that, the pressure transmitter. We're going to find out exactly how these things work.
So, to really wrap our heads around what this gadget does, we first have to understand the problem it's built to solve. We're talking about managing massive, powerful forces that are completely invisible. I mean, how do you control something you can't even see? Just think about it for a second. Our entire industrial world, from factories to power plants, depends on moving liquids and gases through pipes like these. And controlling the force inside those pipes isn't just about efficiency, it's about safety. So how do you measure that invisible force? Well, it all boils down to one fundamental concept.
And that concept is pressure. All pressure is a force that's concentrated on a specific area. The classic formula is pressure equals force divided by area. You know, it's like the difference between someone standing on your foot with a snowshoe versus a stiletto heel. Same force, your body weight, but that tiny heel point creates a ton of pressure. That is the physical property we need to measure.
Okay, so now we know why we need to measure it. Let's meet the little device that actually gets the job done. At its absolute heart, a pressure transmitter is a translator. That's the best way to think about it. It takes a physical thing, pressure, and it translates it into a language that computers and control systems can actually understand. And that language is an electrical signal. It's the perfect bridge between the physical world and the digital one.
And it's not just any old signal. It uses this really elegant industry standard, a 4 to 20 milliamp electrical current. Now, this is a huge deal. It means that pretty much any controller from any company can understand what it's saying. 4 milliamps means zero pressure, and 20 means you're at the max. And here's the really clever part. Using 4 milliamps for zero means that if the signal ever drops to zero, the operators know the wire's been cut or the sensor failed. It's a built-in safety check. This simple idea is what modern automation is built on.
So what is actually going on inside that tough-looking metal case? How does it pull off this incredible act of translation? All right, let's pop the hood and take a look inside.
So when you pull it apart, you see it's not just one piece. It's actually a team of super precise components all working together perfectly. You've got the part that connects to the pipe, the sensor itself, the electronics, and the final connection. Each piece has a very specific job to do. Let's break them down.
Let's start from the bottom, where the action is. First, you have the pressure port. That's the bit that physically connects to the process. Right above that is the real star of the show, the sensor. That's what actually feels the pressure. Then you've got the brains, the electronics module, which does all the translating. And finally, the electrical connection sends that 4 to 20 milliamp signal on its way. The real magic, though, happens in that sensor. At its center is this super thin, flexible membrane called a diaphragm. The best way to think of it is like a tiny, super sensitive eardrum. When pressure from a fluid or gas pushes on it, it flexes just a tiny, tiny bit. And the electronics are so precise, they can measure that microscopic change and turn it into an exact pressure reading. Okay, but this is where it gets really interesting. It turns out that not all pressure is measured the same way. It really depends on what you're comparing it to, and there are three main ways to do it: gauge, absolute, and differential. The two you'll run into most often are gauge and absolute. Gauge pressure measures pressure relative to the air around us, the atmospheric pressure. This is what your tire gauge measures. Absolute pressure, on the other hand, measures pressure relative to a total vacuum, a true zero.
And you can see how brilliant the design is right here. A gauge pressure sensor literally has a little vent that lets the air from the room push on the back of its diaphragm. This means it's always automatically measuring the difference between the pressure in the pipe and the pressure in the room. So if a storm moves in and the barometric pressure drops, the reading will actually change.
Now, compare that to an absolute pressure sensor. This thing is a completely sealed unit. On the other side of its diaphragm is a perfect vacuum, a real, true zero. This means it couldn't care less about the weather or if you're on a mountaintop. It gives you the true total pressure reading every single time, which is why it's so critical for things like scientific research or aviation.
But the third type, oh man, this one is probably the most clever of them all. It's called differential pressure, or DP for short. It doesn't care about the atmosphere or a vacuum. It just has two ports, and it measures the difference between them, P1 minus P2. And this incredibly simple idea, well, it unlocks some amazing new tricks.
So let's check out how this simple concept of measuring a pressure difference lets us measure things that you would never guess have anything to do with pressure at all.
So one of the most common jobs for a DP transmitter is measuring the liquid level in a tank. How does it do that? Well, think about it. The liquid at the bottom of the tank has weight, right? That weight creates pressure. That's our high pressure side, P1. Then the gas at the top of the tank has its own, much lower pressure. That's P2. By just subtracting P2 from P1, the transmitter can calculate the exact height of the liquid. It's basically weighing the liquid to see how much is in there.
Okay, that is pretty cool for measuring something just sitting there. But what about something that's moving? How on earth can a pressure difference tell you how fast something is flowing through a pipe?
Well, the secret is to put a small, carefully designed obstacle in the pipe. The most common way to do this is with something called an orifice plate. It's really just a piece of metal with a very precise hole drilled through the center. And this diagram shows exactly what happens. To squeeze through that smaller hole, the fluid has to speed up. And because of a fundamental law of physics called Bernoulli's principle, we know that when a fluid's speed goes up, its pressure has to go down. It's like a seesaw. One goes up, the other goes down.
And this is where it all comes together. The DP transmitter measures the pressure right before the plate and right after it. You can see the drop here, from 34 psi down to 24 psi. That 10 psi difference is everything. The transmitter's little computer brain knows that a 10 psi drop equals a very specific flow rate. A bigger drop means a faster flow. It is just an incredibly elegant way to measure motion by just measuring pressure.
Okay, let's zoom back out for a second and just quickly recap what we've learned about this amazing little device.
So, what are the big takeaways? 1, it's a translator, turning physical force into a universal electrical language. 2, it does this with a super sensitive diaphragm that works like a tiny eardrum. 3, it can measure pressure in 3 different ways: gauge, absolute, or differential. And 4, that last one, differential, is the secret key that unlocks the ability to measure other things entirely, like level and flow.
So the next time you turn on the tap or flick on a light switch, take a second to think about the thousands of these little translators working silently behind the scenes to make it all happen. Which leaves me with one final thought for you to chew on. Now that you know how we measure pressure, what other invisible forces are being measured all around you right now to make your world work?